Alright, so this is the second video for 6.5, and it's called Logistic Growth. Now, we have used the exponential growth equation to represent population growth. We did that in the last section. Y equals y sub 0, the original population, times e to the kt power. Now, the exponential growth equation occurs when the rate of growth is proportional to the amount present. Now, if we use P to represent the population, then the differential equation becomes the change in P with respect to T is equal to K times P. So the way P is changing is dependent upon the way P is changing with respect to time is dependent on some factor or some multiple of the actual population. Now, the constant K is called the relative growth rate, and it can be found, of course, by just doing a little bit of math here, finding the change in P with respect to time and dividing it by P. That'll give you your K. Now, the population growth model becomes P equals P sub 0 e to the kt, where P sub 0 is the original population or how much you start off with. Now, however, real-life populations do not increase forever. There is some limiting factor, such as food, living space, or waste disposal. We've talked about that. I mentioned it a little bit in the last section. It's called the carrying capacity. There is a maximum population or carrying capacity, M. Now, a more realistic model is the logistic growth model, where growth rate is proportional to both the amount present and the carrying capacity that remains, M minus P. All right, M, remember, is the carrying capacity, the maximum amount you can have, and P is the population of that time. So the carrying capacity that remains is the carrying capacity minus the population. That would be how many more can we put in here before we reach maximum population. All right, then the equation will become dP dt is equal to Kp times M minus P. The change in population with respect to time is equal to some constant times the population times the difference in the carrying capacity and the population. So this is the population, this is the amount of carrying capacity that's left. Well, that's what our equation and our equation says, and our definition just said. Now, we can solve this differential equation to find the logistics growth model. All right, so we'll do our separation of variables there. Move the all the P things over here and move the dt over there, so we end up with 1 over P times M minus P. By the way, M is a constant, so don't forget that, equals K dt. Now, doing some partial fraction here, and that's why we did partial fractions before we got into this, we're going to end up solving this thing. Guys, don't worry about solving this. You're never going to have to solve this for the AP exam. It may be a good idea to know it for college if you're going to do some higher level math and things like that, but other than that, you're not going to. So we find that A equals B and B equals 1 over M, the same way that A equals 1 over M. So we end up with 1 over M times 1 over P plus 1 over M minus P. All they did was factor out the common factor of 1 over M and bring it all the way out to the front. And don't forget, once again, that's a constant. All right, and then we have k dt on the other side. Now we're going to integrate both sides. We can actually multiply both sides by m. That's going to simplify this side over here a little bit. And remember, m is a constant. It's not actually based off of p. So when we do that, we're going to end up, when we take the antiderivative, the antiderivative of 1 over p is natural log of p. Derivative of 1 over, let's say, 5 minus p, because that's a constant, is just the natural log of 5 minus p. And then over here, mk is a constant as well. Take the antiderivative of it with respect to t, you're going to get mkt, and then plus the combined integral constant. So then you can use the product rule, sorry, not the product rule, the quotient rule, or the difference rule for logarithms to combine this into the natural log of p over m minus p is equal to mkt plus c. And then, of course, we can use, we're trying to solve for p, so we can actually go ahead and use the e to exponentiate both sides. Gets rid of the natural log over here on the left, and we get e to the mkt plus c on the right. We can flip them both over. Notice here all we did was change the sign of the power. So this is essentially 1 over e to the mkt plus c. That's what that is. And then we can multiply both sides by p. Actually, sorry, no, what we did there is we divided the p into both parts. So we end up with m over p minus p over p. That's where this 1 comes from. Then we can move that 1 over to the other side. Then we can flip it back over. And multiply both sides by m. So p equals m over 1 plus e to the negative mkt plus c. And of course you can split that e and with the c up, and you can put your a there. We're going to let a, or your original value, equal e to the negative c. Now, I just misspoke, and I need to stop that and clarify right now. I'm sorry, a is not the original value. It's not the same thing as the p sub 0 that we did with the other situation. A is just a constant that we have to find what it is. So it's not going to be the initial value. Be careful. A is not the initial value. It's a value that we have to solve for using the initial value. But this is the logistics growth equation right here. So for instance, with a problem with this, for you to find what A is, you're going to have to know an initial condition. Don't plug it in here, plug it in here. So if you want it, we'll do a problem. Hold on. Let me not get you confused here. All right, so a logistic growth model, we're going to look at 10 grizzly bears introduced to a national park 10 years ago. There were 23 bears in the park at the present time after 10 years. The park can support a maximum of 100 bears. So there's your carrying capacity. Assuming a logistic growth model, when will the bear population reach 50, 75, and 100? All right, so we know our equation. We know the carrying capacity M is 100. And our initial condition, in other words, how many bears there were when t equals 0, is 10. So the population when t equals 0 is 10. And it's 23 bears at 10 years. Now here's the way you need to use this. What you're going to do is you're going to plug in this part first. You're always going to use this. So what you end up with is this. You're going to end up with P sub 0 is equal to, and what do we know P sub 0 is? 10. And that equals 100 divided by 1 plus A times e to the negative mk. And then what's the time? The time is 0. That's the whole purpose, that you've got to have an initial condition when time is 0. Because what does that 0 do to this power? It makes the entire power 0. And what's e to the 0 power? Well, that's just 1. So essentially what you're dealing with is that equation right there. 10 equals 100 over 1 plus a. Now you can go ahead and solve this thing by multiplying both sides by 1 plus a. So you end up with 10 plus 10a equals 100. Whoop, not 1,000, 100. And then you're going to move that to the other side. You get 10a equals 90 because you're subtracting 10 from both sides. Then divide both sides by 10, and a is going to equal 9. All right, so that is one of the unknowns, one of the constant values that you're going to need in this thing. Now, you already know that the 100 is here, and you'll notice that I did not put the 100 in this part, but you're going to from now on. When I wrote down negative, I could have written 100k times 0, and it's still going to be 0. But from now on, you need to put that 100 in there. But we've got to find out what k is. And that's what we do with this part right here. So we use the initial condition to find out what a is. Then we're going to have to go back and find what k is by using some point along the way. How many were in the population at some point along the way? Now, this is the last part where it's really difficult. Once you find what k is and what a is, all you can do is change what t is, and you can find out what those are. Well, actually, no, sorry. You'll actually work backwards to find what those are because you're finding what time that those occur. But you've got to find the a and the k before you can do that. All right, so we've already done this part. We already found that a is 9. So we end up with p is equal to 100 over 1 plus 9e to the negative mkt. So we're going to use that equation with the 9 in place, because that 9's not going to change once we found it, to find out what k is. After 10 years, the population is 23. So 23 here, 10 here, and work backwards, and we can solve this. Now, what happened here was we had this written out. Negative 100 times 10 gives me negative 1,000k. The 1 plus 9e, of course, is right here. And all I did was I multiplied both sides by this whole thing right here, and then divided both sides by 23. Just so you can see it, let me show you. We end up with 23 is equal to 100 over 1 plus 9e to the negative 1,000k. And all I did was multiply both sides by 1 plus 9e. And course, these are going to cancel out. So you end up with this times 23 equals 100, but I'm looking to get this by itself, so I just divide by 23 on both sides. That's where this comes from. All right, and then of course you can move that 1 over by subtracting 1 from both sides. And if you get 100 over 23 minus 23 over 23, you're going to get 77 over 23. Okay, so don't forget, 1 equals 23 over 23. So you get 100 over 23. When we subtract that 1 over here, we subtract it as 23 over 23. So that's where the 77 over 23 comes from. All right, and then we would end up dividing by 9. So 77 divided by 23, and then divide that by 9, you get 0.371981. And then at that point, you need to get rid of the e, so you're going to take the natural log of both sides. When you take the natural log of e to the negative 1000k, you just get negative 1000k. When you take the natural log of 0.371981, you're going to get this negative number right here. Then when you divide both sides by negative 1000, you're going to get a k that's a very, very tiny number here. Now, keep in mind that this whole exponent right here is negative 1000k. So if you take this and multiply it by 1000, you're going to get approximately negative 0.1 times the t. Remember, this negative 1000k came from the t and the k. No, sorry, the t and the m. But then you plug, once you find that thing, that's just going to be the k. So you have the negative 100 times the k. Sorry, that's what gives you this. All right, so at that point, this is the equation that you can use from here on out to find at what time t your population is going to equal the 50 and the 75 and the 100. Now, you can graph this thing. Do not use trace. You can always solve it. But if you graph this thing, you can find out where it's going to be 50 and where it's going to be 75 and where it's going to be 100. Now, what do you notice happens as it gets closer and closer to 100? Well, it flattens out because, remember, the 100 is a carrying capacity. That's a maximum value. So it's going to approach that value, but it's technically never actually going to get there. So we're going to have 50 bears at 22 years. And yes, I did everything backwards when I just pointed that out on this thing over here. We're going to have 75 bears at 33 years. We're going to have 100 bears at 75 years. And at that point, it's actually not going to be 70. It's not going to be 100. It's going to be 99.5. That's the first place that it actually goes to where it's going to round up to 100. Now, if you wanted to solve this or needed to solve this by hand, you could have done 50 is equal to 100 over 1 plus 9e to the negative 0.1t, and you're going to solve for t. So at that point, you could flip both of those, and 1 plus 9e to the negative 0.1t equals 100 over 50, which is 2. Then, of course, you can add or subtract 1 from both sides, and 9e to the 0.1 negative 0.1t is going to equal 1. Divide both sides by 9. And e to the negative 0.1t is going to equal 1/9. Then you take the natural log of both sides. So you're going to get negative 0.1t is equal to the natural log of 1 minus the natural log of 9. And I just went ahead and split that up using the quotient rule. Now, the natural log of 1, of course, is 0. So negative 0.1t is equal to negative natural log of 9. So I can go ahead and cancel my negatives out. The natural log of 9 is 2.19722. And then over here I've got 0.1t. Solving for t, I'm going to then divide both sides by 1/10, which is like doing what? Well, dividing by 1/10 is like multiplying by 10. So t is going to equal 21.9722 years. And you could do that with each one of these and find the answer you're looking for. So that's how you would go about solving it by hand. All right, like I said, not painful.